All of these functions in the enum module work with several different data types. For example, I can pipe a list to the enum module's count function, and it works. I can also pipe a range to the count function, and that works. I can even pipe a map to the count function, and that works as well. I've got a question for you. How many different data types do you think there are that could work with the enum module? Yeah, that was kind of a trick question. In theory, you could use an infinite number of data types with the enum module. So what do I mean by this? Well, with a bit of work, you can make almost any data type compatible with the enum module. To further explain what I mean, I'm going to walk you through a little thought exercise. Imagine for a moment that the enum module doesn't exist, and you and I have been tasked with creating a generic module sort of like the enum module, but for now, to keep things simple, our module will only have the sum function. We're going to call our module the calculate module. Let's start by implementing a sum function for a list of numbers. So to start, I'll create a named sum function that takes a list. Now, as you know, there are no loops in Elixir, so we'll need to solve this using recursion. What I'll return from this function clause is a call to a new doSum function that takes a list, and I'll pass in an initial value of 0. Next, I'll create a doSum function clause that handles the base case, which is when we're dealing with an empty list, so I'll pattern match the first parameter on an empty list, and I'll bind the second parameter to the total variable, and in this case I'll just return the total. Now I'll create a doSum function clause to handle the recursive case. For the first parameter, I'll pattern match on a list, but then I'll destructure the head of the list from the tail of the list, and I'll bind the second parameter to the total variable. Next, I'll make a recursive function call to doSum, but this time, I'll pass in the smaller list as the first parameter, the tail, and I'll pass in the result of adding the value from the head of the list with the running total. Okay, this should do the job. Let's try it out by opening IEX and loading our script file. Then I'll call our calculate module sum function and pass in a list of numbers. And as you can see, it worked. Cool. Let's take a moment to think about how we're starting to implement the sum function. This module that we're working on is meant to be a very generic, general-purpose module that many other Elixir programmers can use, kind of like the enum module that we're pretending doesn't exist. Now, let's change hats for a moment. Imagine for the moment that you're not the author of the calculate module, and instead you're an Elixir programmer that would like to use the calculate module in one of your projects. But here's the thing. You want to use the calculate module's sum function on other data types in addition to lists. So for example, you'd like to use it on a range, or maybe maps, or tuples, or structs. Okay, so how exactly is our new calculate module going to work with other data types? Well, we could implement the sum function kind of like we did with lists, but for maps and ranges. In other words, we could write more doSum function clauses, like these, that would handle the data types that we anticipate people would want to use, such as ranges and maps and so on. But we'd still be left with a big problem. So what's the big problem? Well, there's just no way for you and I to know all the different types of data that people might want to use with our sum function. Now, for discussion's sake, let's say we can anticipate all the different data types that people would want to use with our sum function. I mean, it's not actually possible, but let's pretend it is just for a moment. So following the pattern we've started here, we'd need to write more doSum function clauses for all the different types of data that we want to work with our sum function. Does this seem like a good, simple, generic pattern to follow? I'd say nope, not really. We'd have to write tons of different doSum function clauses for all the different data types we want our sum function to work with, and in truth, we can't know all the different types of data people may want to use with our sum function. It's just not possible. So is there a better way? What I mean is there a more general purpose way of implementing our sum function so it can work with any data type, even data types that you and I know nothing about? Well, yep, there is. This is where this thing called protocols comes in quite handy. So what exactly is a protocol? Well, it's a way of enabling extendable polymorphism in Elixir. What do I mean by polymorphism? Well, many people know the word polymorphism from object-oriented programming, but polymorphism in Elixir is different than this, though the root meaning is similar. The word polymorphism has a root meaning of many forms. And when I say polymorphism in the context of the sum function, I mean it should work with many types or forms of data. Now, truth be told, you don't technically need protocols to make a function polymorphic. For example, we could just add a few more function clauses to our current implementation to handle ranges and maps and so on. And if we did this, you could still call the sum function polymorphic because it can handle many forms of data. So if this is true, why do we need protocols? Well, because with protocols, we get extensible polymorphism, the key word there being extensible. When I say extensible polymorphism, what I mean is any old Elixir programmer can use a protocol or implement a protocol to make their custom data types work with our sum function. You'll see exactly what I mean by this in just a moment. Okay, so how do protocols work? Well, in its simplest form, it's a three-step process where you define a protocol using the def protocol macro, then you give it a meaningful name of your choosing, then in the do block, you add one or more function heads, specifying the name of the function and its parameters, but you leave off the body of the function. Defining a protocol with a def protocol macro is typically the responsibility of the library creator, not the consumer. All right, so what do you do with this protocol? Well, the next thing you do is create an implementation of the protocol for different types of data. The way you do this is by using the def impl macro. Then you specify the protocol you're implementing, and you specify what type of data the implementation is for. Then you write an actual implementation of the functions specified in the protocol's definition for this specific data type. Implementing a protocol with the def impl macro could be done by the library creator, and it can also be done by consumers of the library as well. Now, once you've got a protocol and at least one implementation, you can call the function by keying the protocol name dot whatever the function name is, and you can pass in the required parameters. Okay, the mechanics of creating and implementing and using protocols isn't too hard to understand, but the benefits of using them might still seem a bit fuzzy, but hang with me and I'll try to clear things up. Let's go create, implement, and use a protocol in our calculate module. So I'll start by creating a new protocol named calculatable, which has one function in it named sum, which takes a single parameter. Next, let's go create an implementation of the calculatable protocol for lists. So how should we implement this? Well, actually, we've already implemented it up here in the calculate module. So let's just move the implementation from this module into the protocol's implementation. Now, we need to create another sum function in the calculate module, which takes some data, and we'll just call the calculatable protocol's sum function and pass along the data. Okay, so in summary, we created a new protocol here. We then created an implementation of the protocol for lists here. Then we're calling the sum function via the new protocol here. Let's try it out just to see if it's working. So I'll open up IEX, including our script, and I'll call our sum function, passing in a list of numbers, and it works. Cool. Now our sum function won't work with a tuple, as you can see here, but we can fix that by creating another implementation of the calculatable protocol for tuples. Then we'll create a sum function that takes a tuple, and I'll implement this by piping the tuple to the tuple module's toList function. Then I'll pipe its result to the calculatable protocol's sum function, which is essentially having this protocol implementation sum the list. I'll go ahead and recompile the calculate module, and I'll try calling sum with a tuple of numbers, and it works. Cool. Now, since we're using a protocol, our library is extendable to any other data type. So for example, let's change hats again, and let's think about consuming this library with unique data types like a struct. If we had a struct named polling locations, and we wanted to use it with our sum function, we just need to create an implementation of the protocol for our struct. Okay, there's a couple more things you might be struggling with in this example. Let me explain what I mean. First of all, you might be thinking to yourself, implementing a protocol for my own custom type doesn't really save me any lines of code. I mean, the code I write for the protocol's implementation could have just as easily been written in the structs module, so why would I implement it as a protocol? And another question you might have is, why have the calculate module sum function at all, since I could just make a function call by keying calculatable.sum and passing in the data? Well, let me give you a better example of protocols that should answer both of these questions. Let's turn back to the enum module for just a moment. The enum module has a bunch of useful functions, and all of these functions work with any data type that implements the enumerable protocol. So let me ask you this. If you had to implement the enumerable protocol on one of your own data types, how many functions do you think you'd need to write in the protocol implementation? Well, based on my simple example in this video, you might be inclined to think you'd need to write an implementation for every single one of the enum module's functions, but you don't. If we peek at the docs for the enumerable protocol, you'll see that there are only 4 functions that must be implemented: reduce, count, member, and slice. So basically, if you implement these 4 functions for the enumerable protocol, you get to use all of these functions from the enum module. That's a pretty good trade-off, right? Basically, you get to write 4 functions to implement the protocol, and you get to use over 95 functions as a result. Now, you might be thinking, how is this possible? Well, I said something a while back that's worth repeating as it explains how this is possible. What I said was, the reduce function is the most powerful function in the enum module. In other words, you could replace every single one of these functions in the enum module with the reduce function. So it stands to reason, if you implement the reduce function, you can get most of these functions for free. Okay, in the next video, we're going to take a shallow dive into macros.